you guys, Negar and Noushin. So, hello everyone. Thank you so much for joining this workshop. I know everyone is very excited about it. I have been reading all the Slack comments that everyone is looking forward to this workshop. So today we have two wonderful coaches with us. We have Noushin and Negar to run us through this malware analysis session. Just to give a bit of background, so Negar is security researcher at Microsoft, and Noushin is senior security researcher at Kaspersky Labs. So thank you so much for taking out the time to doing this workshop with us. Before I hand it over to you guys, I just want to make sure and let everyone know that this session is going to be recorded. And also we want this session to be as interactive as possible. So if you have any questions, just feel free to send in your questions in the chat window below. And we have Maeesha, who is co-moderating with me, and she'll be looking at all your questions and forwarding them to Negar and Noushin for them to answer. And we also have from AWSN, Suzanne, who will be making sure that everything from Zoom perspective is running smoothly. So with that, I think I will hand over to you, Noushin and Negar.
Hello, everyone. Hello, everyone. Thank you for the introduction. Just for you guys not to get confused, we are twin sisters. I'm Noushin with the blue jacket, and I'm Negar. Yeah, Negar with the purple jacket. So we are going to learn malware analysis together. This is the first workshop session. For this session, we are not going to use any tools and any like analysis labs, lab like environment. We are going to see some stuff on our screen. You will see the slides. So little bit of background. We both have started doing reverse engineering and malware analysis. I think it was around like 8 years ago. We used to work together for a company, for an antivirus company, as malware analysts and security software developers. But then after a few years, I joined Kaspersky Lab, which was then called Kaspersky Lab. Now it's just Kaspersky. And Negar joined Microsoft. I actually joined Microsoft recently. Before that, I was with another company doing more like consultancy, doing more application security and pen testing jobs. So let's start. And please feel free if you guys have any questions, just first type it in the chat box, or just say you have a question, so we can stop talking and you can unmute yourself and ask your question. So for today, we want to first start with talking and some discussions about the safe environment for malware analysis, what that means, and why we need to use an environment and how it can help us. Then we will say some basic reverse engineering concepts to get us a bit more like warmed up for the rest of the session. And we will have a short like crash course of x86 assembly, and then we will look at some code examples and we will discuss together what the code does and what's the logic behind the code. And we will, of course, talk about why we picked x86 assembly for this course. So let's start with the environment. Can I just say something? Just before we actually start learning about reverse engineering, how many of you had any experience in assembly or reverse engineering? Yeah, you can say in chat. Okay, so it's good. Some people, social investigation is this reverse engineering, can have reverse engineering tasks, of course.
A lot of them do not have any experience.
Okay, so no worries. Someone was at our CC workshop.
Yeah.
It's going to be quite similar, but anyway, it might be useful to hear it again. But don't worry if you never had experience in malware analysis. We are going to start from the beginning. So let's talk about the safe environment. So basically, we usually use a VM on our machines to do malware analysis, but it's also possible to use a separate machine to do malware analysis and to do research. It has its own benefit and it has its own problems. Mostly, it's more difficult and more inconvenient to do malware analysis on a separate machine. Because you might get your system infected and you need to reimage the operating system every time, and it's not very easy or very convenient to do that. So that's the main reason we use a VM. But apart from being convenient, first of all, it helps you protect your system, your main machine that you do your day-to-day job or your like personal web browsing or watching movies or whatever you do on your system. And of course, your personal data um, from being touched or being accessed by a malware or by an attacker that might get access to the system. That's the first reason. The second reason is controlling the code execution. What that means is that when you run the malware code, the malware on a separate system, on a virtual machine, it's much easier to control the code execution. You can stop it, you can use a debugger, you can stop the code at some point, you can change the program execution flow, you can run it multiple times. You can change the environment setting and see how the code execution flow changes. So basically, you can have full control over the code execution. Third reason, customizing the OS resources and network settings. So as I briefly mentioned this, it's much more easier to customize the system settings when you use a VM. You can easily change the memory and RAM capacity. You can easily change the network settings. You can add different network adapters because this is a virtual network adapter. It's not using actual new hardwares. You can disconnect the system from network. You can just share the network with the host machine. You can change the operating system completely. You can use different operating systems. In parallel, you can have like two Windows operating systems talking to each other, two Windows VMs. You can have a Windows VM and a Linux machine talking to each other. So you can do whatever you want in terms of having like different system settings, which is not possible on the real machine. And last but not least, using snapshots to save and restore specific system states. So basically, when you use a VM, you can just create a snapshot at any point of the execution of the malware. Like imagine if you are debugging something that's a bit more complicated and you get to a point that's interesting for you, you want to come back later and maybe like change a flag or change something in the memory and see what it does if that changes. You can just create a snapshot and then return to it, or you can, or it might be like long process. You can just stop at some point, take a screenshot, and then restore later. So basically you can have like many snapshots from the system when you are doing the analysis, and you can restore them and revert to any of these snapshots whenever you want. There's a question here. How do you guys import the malware samples into the VM? So basically what we do is to create, if you've ever worked with a virtual machine, it doesn't matter if it's a VirtualBox VM or it's a VMware VM or any other system, any other application that you use, you can just create a shared folder and put malwares to the shared folder and take it from the shared folder inside the VM. But what is more important is that we usually, most of the times, we disable any security software inside the VM. Like if you use the Windows VM, you disable the Windows Defender, or like the firewall, or if you have any other antivirus installed on the system, on the VM machine, you disable that. And then we put the malware in a password protected zip folder. We put it on the shared folder because we don't want our host machine's antivirus to detect the malware and delete it. And then we only copy and extract the malware from the zip file inside the VM. Let's move on. Let's have a look at the registers in a system. So basically in a 32-bit system, we have 32-bit registers, and what the registers are basically memory blocks of like the basic blocks of memory that system uses to handle different instructions and handle different programs. We have different types of registers. The registers are memory blocks in the CPU, and they are used to accessing like different values more easily than going back and forth to memory and read everything. So there are like different types of registers. We have common registers that are used for like common purposes. They can be used for any purpose, but some of them have like specific purposes as well, which we will see a bit later. So in a 32-bit system, all the registers are 32-bit long. We have these names for the common registers: EAX, EBX, ECX, EDX, ESI, and EDI. They can be referred, the registers can be referred to by their names, or they can be half of the register or one quarter of the register can also be referred to based on the names. So the lowest 16 bit of each register is called AX or BX or CX, DX, SI, and DI. And even in the lower 16 bit, we can access the upper 8 bits or lower 8 bit with the names AH and AL, and like according to this scheme we can access all the common registers as well, except for the ESI and EDI, which can only be referenced for the full register or for the half register. So some, as we said, these are common registers, but they can have like specific purposes as well. Like for example, EAX has a very specific purpose, and it holds the return value of every function. So when a function is called, when we return from the function, EAX register always holds the return value of that function. It's also quite important to keep in mind. Also, with the ESI and EDI, these two registers are commonly used for working with arrays and strings. So they are more common when we handle like long strings or big array of characters or bytes or whatever, like hex values, compared to EBX and ECX and EDX. We have other registers, which are again 32-bit registers. These are not common registers. They have a specific purposes on the system. We have ESP, which is extended stack pointer. We have EBP, which is extended base pointer, and we have EIP, which is extended instruction pointer. I'll explain what each of these registers do. But there is a question in the chat window. Sorry, which one holds return value of every function? That's EAX. So let's go up again. EAX, the first one, the first common register here. This is the one that holds the return value of the function. But it's not the only purpose of EAX. It can be used for holding any other data.
So, no worries. So these registers, the first two, ESP and EBP, they work with the stack. So ESP always holds the value of the top of the stack. So whatever whatever value needs to be pushed onto the stack, the instruction need to access ESP value to understand what's the memory, what's the address of the top of the stack. Whatever needs to be popped from the stack, again the same. We will learn about the stack frame and how stack works in more details in the later slides. But here we just wanted to talk about the register that holds the top address of the top of the stack. And then we have EBP, which is again a register that holds the memory address in the stack,
but this memory address is the base pointer. What the base pointer is, it basically shows the beginning of the stack frame for a single function. So during the execution of each function, the EBP value doesn't change because it always holds the base address of the function stack frame. And we have EIP, extended instruction pointer. This is another like specific register with a specific purpose. This register always holds the address of the next instruction to be executed. So when the program starts, when the system starts executing a program, how it handles the execution flow and goes to the next instruction, like instruction after instruction, it looks at the EIP value and finds the address of the next instruction to be executed. So this means that it either, at each point of the time, it either has the address of the next line of the next line instruction, or if we are dealing with a jump or with a conditional instruction, it might hold the address of some like far memory address of the program. So before moving to stack and talking about the stack, any questions regarding the registers? Please feel free to ask any questions if you have. We have quite a lot of things to learn, and at the end of the session we are going to see some code examples which requires you to understand all these parts. So if there is any question, please feel free to ask. Okay, so if there's no question regarding registers, let's have a look at the stack frame and stack layout. So the stack, as I'm sure most of you know how a stack object works. Stack is like a stack of plates. You put a plate on top of the stack or take a plate off the top of the stack. So it works the same in the memory of a program. Whatever is, it's like it's a first in, last out. Whatever is pushed into the stack is placed on top of the stack, and whatever is popped out of the stack is it's removed from the top of the stack. So you can either push or pop values from the stack. And then when you look at this slide, you can see that we have higher memory addresses, we have lower memory addresses on top, and the stack frame is, the stack layout is basically prepared based on the stack frames of different functions. So we have the stack frame of one function, and then on top of that we have the stack frame of a function that's been called by that function, and on top of that we have the stack frame of the next function that's been called inside the other functions. So current stack frame, on top of the colors the stack frame, on top of the colors stack frame. And again, as it can be seen here, stack grows up towards lower addresses. So what is a stack frame? We talked about the colors, the stack frame, colors, the stack frame, current stack frame, but what is the stack frame? So a stack frame is basically a part of the memory of the stack that holds the input arguments of a function, holds the return address for the colors function, and holds and have some space for the local variables of the function. So when a function is called, before the function starts, we need to give them the input arguments, right? So basically what it does, what what you can see when you open a program in a debugger. You can look at the instructions, and you can see what the stack frame, how the stack frame is changing. You can see that input arguments of the function are pushed into the stack. So for example, in this example, we have a function with 3 input arguments. First of all, the third input argument is pushed into the stack. Then the second input argument is pushed into the stack. And then the first input argument is pushed into the stack. And after this, when the function needs to be, when the execution flow needs to be moved to the calling function, the function that's been called, it needs to know where it requires to return to. So after input arguments, the return address is pushed into the stack, so the function knows where it needs to go back. And then we have the old EBP. If you remember, EBP was the base pointer of the function. So we have the old EBP because when this function needs to return, we need to have the EBP for the caller function reserved somewhere. So we need to push it into the stack. And then at this point, EBP, which is the base pointer for this function, is set to this memory address. Then the stack pointer moves upward to make some room for the local variables of this function. And then, of course, when the function ends, after everything that needs to be happen inside the function happens, and the function needs to return, it returns to the return address that's been saved in the stack frame. And the old EBP is also replaced the current EBP. So as I said, pointer, and as it's clear from, it can be guessed from its name, it is a base address. It's not going to change throughout the function flow. So if at any point in the execution of a function, the program wants to access any input argument or any local variable, it's easy to use relative addresses compared to EBP, because EBP is not going to change. So EBP plus 4 is always the return address. EBP plus 8 is always the first input argument. And of course, on the other hand, EBP minus 4 is the first local variable. EBP minus 8 is the second local variable, and it goes on. Of course, there are functions that don't have any input argument, so you won't see any input argument in the stack frame. There are functions that might not have any local variables. Again, you wouldn't see any local variable. So this like 0x14 that you see here is not always it's not always the case. Sometimes you only need 2 local variables. It depends on the program. So questions? Okay, very good. So let's move on. Let's now learn some x86 assembly instructions. So why x86 assembly instructions? Because most of the malwares these days are written for Windows operating system, and this is the instruction set that's been used in Windows operating system. We can do like reverse engineering on Android malwares, or on malwares written for small devices, like malwares written for ARM architecture or MIPS architecture or any other architecture. They require their own like knowledge and their own maybe new workshop. But for this workshop, we picked this one because this is more common, and it's basically the basic assembly language that a malware analyst or a security researcher needs to learn. So can you please suggest some resources to learn registers, stacks, etc.? So there are some very good books for beginners in malware analysis. We can recommend those books, but talking about our own experience, when I want to learn more about something, the first resource that I go is either the main vendor that provides this architecture or this information, or Wikipedia pages, but you can use, someone said YouTube, you can use YouTube videos. Of course, it's not something very uncommon. You can find out about x86 registers and stacks in many websites and YouTube videos, but there are some very good books for malware analysis, starting the malware analysis journey. We can give
I'll
you
put
the
the
names.
name of the books in the chat box.
You recommend Flare and Coco VM to analyze malware. What about Kali? So, talking about the any environment that provides like tools to do debugging and disassembling and keeping logs and monitoring tools are good to do malware analysis. But my suggestion, our suggestion, is to create your own lab. Try to play with it and play with some malwares and learn what tools you need. Do you need like a tool to capture network traffic? Do you need a tool to look at the network connections? Do you need a tool to look at the how processes are created and killed on the system? And then over the time you find out what tools you need, and then go for the most common and most tested and used tool in that area, and put it on your VM. We usually use the labs that we prepare ourselves with the debugger and disassemblers that we are quite like comfortable with. Do you use sysinternals? Yes, sysinternal tools are very good for doing like dynamic analysis, running like how it happens in a sandbox. You run the malware and just look at the logs. You can do it a bit more manually on your own system. You run the code and you use like some of the tools from sysinternal suite to monitor changes in the registry keys, changes in on the system, like based on the process ID or process name. Look at different processes, look at different like file creation and like accessing files, writing on the files. Sysinternal tools are quite good. What about Kali? Kali is also good. The problem is that most of the times we work on Windows malwares, and to be able to work with the Windows malware, work with any malware for any architecture. Like for example, if you want to debug a malware, an Android malware, it's much easier to do it on an Android system. So for Windows malware, it's much easier to use a Windows machine to to see everything, to let everything work as it's supposed to work.
Okay. I'm gonna give you some resources like good books. Do you want to add anything?
So these books, sorry, we didn't put the names of the authors, but these are like the most common books recommended for beginners in malware analysis. First of all, the first one, practical malware analysis, is very good. It has all the information you need about the memory layout, about the stack, the instructions, and it goes on to common malware techniques, common tools to use for malware analysis. It's very good, and it has like different different practical challenges and tests as well. To be honest, I haven't done the challenges and worked on the exercises myself, but the book is very good.
Yeah, I believe it has everything you need to know to start malware analysis.
And then the other two books, they have like more overview of the other architectures. I'm not sure which one, maybe the second one, The Secrets of Reverse Engineering. It has a little bit of ARM. It has a little bit on the kernel analysis and so on. So yeah, you can start with the first book, and then the other books are a bit more like practical. The first one has more like theory and the concepts.
Okay. Any other questions? Okay, let's learn about like common instructions. Okay, so most of the instructions that we work with are one of these types of instructions. They can be either the first one, which you will see an operation code and two different operands, like add instruction, which takes one register and one immediate value, or maybe two registers, and the other one which is an operation code and one operand, which is an instruction which takes just one operand, like pop edx, which pops one value of the stack and puts it in edx register. These are the most common ones, the most common basic x86 operations. Add, which takes destination and source. Sub, which takes destination and source as well. So these are just addition and subtraction, just doing mathematical add and subtraction. For example, the first one, the add instruction, it takes first destination and then source. It adds the value of the source to the destination and puts the result in the destination. Same for the sub. It subtracts the value of the source from the destination and then stores the final output in the destination as well. The next one is dive, idive. It's for division. Mol, imol. It's used for multiplication. And then and, or, XOR, and not. These are the logical operations. And takes destination and source as well. It does the logical and. It ends the source with the destination and again puts the result in the destination. The same for or. It does the logical or, and then XOR, which is exclusive or, and not, which takes just one operand and negates the value of this operand and puts it in the same register as well. Some other operations, move, which also takes two operands, destination and source. It moves the value of source to the destination. Move SP, which is used for moving a byte from source string and puts it in the destination string. Move SW, which moves one word from source string to destination string, and move SP moves one D word.
I jump in for a second just to explain a little bit what word and D word are, in case you are not familiar. So basically, byte is one byte. Word is a memory address that holds 2 bytes. So word is equivalent to 2 bytes together, and D word is for 4 bytes or 2 words. So then we have the next instruction, which is load LEA, or load effective address. It loads it treats the source operand as an address and loads the value of that address to the destination.
Next operations, pop, which takes one operand, push, which can take a variable or a register, call, and read. These 4 operands work with the stack, as Noushin mentioned earlier and discussed how pop and push works. They work with the stack, and also call, which we already learned how it handles the stack. It creates the stack for the calling function, and then read, which is return, which also works on the stack. There are some different jump operations, JMP, which all take one address as one address. JMP is just unconditional jump. The execution flow jumps to the address, to this address when it reaches this instruction. JZ, which is jump 0, it checks the 0 flag, and if the 0 flag is set, it jumps to this address. JNZ, which is jump not 0, it just jumps to this address if the 0 flag is not set. These two works opposite of each other. JL, which is jump less, it checks, it usually comes after a comparison. If the first value is less than the other, it jumps to this address, and jump less or equal. If the comparison is less than or equal, it jumps to this address. And I just mentioned about these flags. In here, when you look at the 0 flag or some other flags, these 4 flags are different parts of one register, but because they have different purposes, we look at them like this. 0 flag, these are the different bits of one flag. 0 flag is it just checks if it's set when the arithmetic comparison is made. Correct me if I'm wrong.
Okay. Let me explain this a little bit. We will learn it a bit more when we look at the code examples and when we look at the malwares inside the debuggers. But yeah, we have 0 flag, which is set when an operation returns 0. We have sign flag, which is set when an operation has a positive result. We have overflow flag, we have carry flag, we have other flags as well. They have their own purposes and their own meanings.
but these are all parts of one, just one more register on the system. So any examples, sorry, any questions before we move to the examples? So if no questions, if everything is clear, so now we want to have a look at a few code blocks of code. We want you to take a few minutes on each of them. Try to see if you can understand what every single line of the code does, and then we will discuss it all together.
And if you can understand the main purpose of this code snippet, that would be good.
Because it's actually our main goal to understand at the end what was the purpose of the code snippet. So first code example is this. Let's take maybe 5 minutes.
And also there is nothing in this sample code which we are not familiar with. It's just push, move, and stop instructions.
So let's take like 5 minutes. Try to remember what you have learned so far about the registers, about the instructions, and then we will start discussing together what it does. In the meantime, if you have questions, just feel free to put it in the chat, or maybe like unmute yourself and talk.
We are going to put ourselves on mute if you don't have any question at the moment, so you can take your time.
In the chat, what do you think about?
Share with the others if you understand anything from this code, or if you have any questions, so someone else might have answer for it.
But if it looks very strange and you don't understand a single line of the code, let's discuss and see why is that.
So anyone wants to explain what this code does?
Sorry. Yeah, we want someone to start explaining what they think this code does. What the first, even like the very like basic stuff that we discussed earlier, what the push does or what the move does. Can someone just unmute and volunteer to speak about the code?
I can try.
Sure.
Yeah, of course.
So EVP is the base pointer, and it is pushing the value of the function into ESP. That's what I'm thinking. I don't have the answer yet.
Okay, so.
And then it is subtracting. Yeah, I'm not sure about the last one. So I'm trying. If anyone else wants to try, please go ahead.
Okay, that was a good try.
Yeah, that was a good try. Very good, thank you. Someone also said save the EVP, then set EVP to point at different position in stack. The sub is to save space for the variable. Okay, that's good. Copy ESP into EVP. That's also good. So all of your explanations are quite relevant and quite right. So basically, we have learned earlier what EVP and ESP does. So the EVP register would hold the address of the base pointer for a function, and ESP would also hold the address of the top of the stack. What push EBP does, it pushes the value inside the EBP register on top of the stack. So if you remember, we had something that resembles this in one of the slides. There was the EBP, which we had called it old EBP, placed into the stack at some point. So copy ESP into EBP, EBP points the stack frame. Okay, so then we move the value from ESP to EBP. What this does. So ESP, as we know, holds the address of the top of the stack. When we move the value of ESP to EBP, this means that we are setting the EBP, which is the base pointer, to the top of the stack. So we are setting the value of the EBP. So basically what the first two lines mean is to save the old EBP and create the new EBP. And the last one, sub ESP 10H. What is this 10H? It means just 10 hex. So what it does, it moves the stack pointer ESP 10 towards like lower addresses, as we learned that stack grows towards lower addresses with the value of 10. So it makes some room for the local variables. So yes, it decrements the stack pointer by 10, but basically it makes room for the variables because we learned that the stack grows towards lower addresses. So every time a value is pushed on top of the stack pointer decrements for the like four offsets for holding one 32-bit value. And every time that something is popped off the stack, the ESP value just increments by 4. So let's go up, let's have a look at this one, oops, sorry. This one here. So actually, I don't know why there is a strange green line at the middle of the slide. But anyway, so basically, let me see if I can point. Can you point on something on the screen? Oh, you can see my cursor. Okay, right. So here, the old EBP is pushed on top of the stack, and then the address of the EBP
Is everything all right?
I think
Yeah.
I have some issues with my network.
No, we are able to hear you and see the screen properly.
Okay, good. So maybe it's the problem with Negar's laptop, because we were looking at my screen through Negar's laptop, and the video was like freezed at some point.
No, everything is all good. We're able to hear and see the screen properly.
That's good. So here at this point of at that code, we were at this point of creating the stack frame. So the old EBP is pushed on top of the stack. The ESP value, which at that point is here, points to here, is moved to the EBP. So the EBP value is set, and then ESP is 10 was subtracted from ESP, and some room is created for the local variables. So does it make sense?
Is that clear for everyone what this sample code does?
Okay, so if no questions, let's have a look at the second code example. So this one. So let's again take a few minutes. In the meantime, if you have questions, feel free to put in the chat or just unmute and raise the question. Or if you have any comments or you want to explain something, feel free to do so. We want to discuss this sample code together.
Yeah, and if you have any idea what this code does, or even just one line, then you can share it with the others.
So any ideas what that bracket means in the first instruction? So Cap is asking what is test. So test is basically an instruction that, so first of all, to make it a bit more clear, the instruction set, the x86 assembly instruction set is quite huge. We covered only the main, like most common instructions. So you will see a lot more instructions in real programs when we look at the programs. Even in this sample code, we have one new instruction. In the next sample code that we are going to look, which is the last one, we have different new instructions. Test is just a comparison between two operands. But if you come across a new instruction, you can just Google it and see what this instruction is, or there are like x86 assembly references from Intel. You can download that. We might have a link to that. You can share it in the chat. You can just go later, download the full instruction manual and then use it as a reference whenever you encounter a new instruction.
But did you explain what test does?
Yeah, test does comparison between two operands, and then sets the flags, zero flag, carry flag, overflow flag, based on the comparison. No worries. So any idea what, can someone just explain what the first line of the code does? Any idea, anyone can guess what that bracket means? Nothing? No one wants to guess something? Pushes the value of EBP minus 4 onto the stack. Okay, so EBP is a register which holds the value, and then it is subtracted by 4. But what that bracket is, what does that bracket do? So the bracket, what the bracket does, it points to the memory address that EBP minus 4 holds. So EBP, if EBP holds an address, when you subtract 4 from that address is another address. So if you don't use the brackets, what is pushed on top of the stack is the address. But when we use the bracket, what is pushed onto the stack, on top of the stack, is the value that is in that memory address. Make sense? So, and just to explain this a little bit, this sub underscore 400 100 it's just a name. It means subroutine, which is just a function, and this 400 100 is the address. You can see here as well with loc underscore 41 0011. This is again another memory address on the on this program memory space, and this just means location. So when you use a disassembler or a debugger, it can understand when at which address of the memory there is a function, and at which address it's just a piece of code. So when there is a piece of code, it's just called with location. It's just like reference with location underscore the address. And when we deal with a function, it's like a sub for subroutine underscore the address. So far we found out that there is some value that's been pushed on top of the stack, and we know that EBP-4 holds a local variable of the current function. So one of the local variables of the function is pushed on top of the stack, and then what happens here, we have a call to a new function. So basically this means that the local variable, one of the local variables of this current function is passed to this function as an input argument. And then the call instruction, which moves the execution flow from this current address to the address of the new function. So here we don't see what this function does, we don't see the code, but we see the next instruction, which is test EAX. Anyone, any idea what this is? Why would you just test EAX with EAX after a function? So you guys remember what was the specific purpose of EAX register on top of the like common purposes of EAX register? Okay, compared to two operands in EAX. So basically EAX can hold only like one value at a time. So when we have EAX and EAX, these are basically the same thing, the same value. And test EAX tests if the value of EAX is 0 or not. But why EAX? What is interesting about EAX here? Why would you check the EAX value? Anyone remembers? What does EAX do?
Why would you check EAX after the call?
What?
It's just a hint.
Yeah, why not EBX? Why not ECX? Why EAX? So basically when we talked about the registers, we mentioned that there are common registers, which were EAX, EBX, ECX, EDX, ESI, and EDI. And we said that some of them have a specific purposes as well. EAX was one of that common registers that had a specific purpose, and that specific purpose was to hold the return value of a function. So whenever you return from a function, EAX holds the return value of that function. So what this means is that after this function is called, we check the return value of the function by using test EAX.
And then this test instruction sets the 0 flag.
Sets the 0 flag and prepares the system for the next instruction, which is a conditional jump and the condition is based on the 0 flag. So this J and Z basically means jump not 0. So it means that if the 0 flag is not set, jump to this location. If the 0 flag is set, just continue with the execution.
Is that clear what this piece of code does?
So this piece of code basically passes a value to a function and then checks the return of the function, and as like as a condition to move to a new section code or not. It's basically like saying if this function with this input argument do something, else do something else. Make sense? Any questions? Is it clear or not?
So let's move on to the next sample code, which is a bit more complicated, but I guess we have enough time to have a look.
So next code example is this one.
The whole context. Okay.
So this piece of code, you can see here the label for the address of these instructions. You can see it's similar to what we learned earlier, location something something, location 10001000. This is the address of this instruction. Just because we don't have a lot of time, just give you some hints. MoveSP, if you remember, was used to move 1 byte from the source to the destination.
And for some strings.
So here, as you see, even here you can see that the reference shows says byte PTR. So it means that from this pointer, choose 1 byte. And then we have roar here, which is rotate right, a new instruction for most of you guys. And we have int, which is increment. It just increments. We have add, we have compare, and we have JB, which basically means jump below. So we want some volunteers to start explaining what different, like what every single line of code does. Even if you want to explain the first line, please feel free to speak, and then we can move to the next line. First line, can someone explain what the first code instruction does? Anyone wants to try? No one? It's not that difficult, it's just a move, and I explained a little bit. Move single byte, it just moves 1 byte from the source to the destination. What this means, we have learned that this bracket means accessing the value at that address. So basically there's an address that is created from adding the value of ECX register and ESI register to each other, and 1 byte from this address is copied into EBX. Make sense? Okay, so next rotate right. So we don't want to get into the details what rotate right does, but it just it basically changes the value based on the binary representation of the of a value. What it does, it rotates the value, it rotates right the value of EDX register 0D times, which is 13 in decimal. So it rotates the value, the binary value of the EDX with 13 to the right. So it might sound very complicated, but we don't care about it that much. What is important for us is that this EDX value is changed somehow. What is the next instruction?
It's just simply increments E6 value.
Can someone guess up until here what is this ECX? We have seen ECX in the first instruction as well, and it's been incremented here. Any idea what that is? So let's go a bit further. Then here we have add EDX EBX. The EBX value is added to the EDX value here. Then we have a compare instruction, compare ECX with EAX. And then we have,
How can we get rid of that? This one.
just a second. It's a bit strange. Okay, so we have compare ECX with EAX, and then we have jump below. And jump below jumps to a memory address, which is 10001000. Any idea in general, not in the specific like lines of the code, what is this piece of code in general? Like only looking at maybe like the first, like the last instruction and the addresses, memory addresses. What is this? What does that mean that it has a location here and there's a jump below at the end with some location, with some address? Any idea? It's a loop. It keeps jumping to itself. Perfect. Yes, it's a loop. So it jumps up again if JB condition is met, and JB is jump below, and we have a compare instruction before that. So basically it means that if ECX is below EAX, jump up. So if it's a loop, what is the return or the end condition of the loop?
So we know that this loop depends on the comparison of ECX and EAX. So this instruction controls the loop, right?
And
so can someone guess what ECX is now? Based on those three lines that has ECX in, can someone guess what is ECX? What does ECX do in here?
So as you see here, we have increment ECX, the third line of the code. We have increment ECX, and then we are. So basically in every iteration of the loop, we increment ECX by 1, and then at the end, at the loop condition, we check if ECX has reached EAX. and if it has not reached EAX, so if E6 is still below EAX, it jumps up again. So this means that ECX is the counter of the loop. And this counter is used in the first instruction as well. There is byte PTR ECX plus ESI. So ECX is incremented every time. So can someone guess what ESI is and what ECX is here?
Come on, we're running out of time.
So basically, if you imagine ESI is the beginning of an array or a string, because we are not changing ESI at all throughout the code, but ECX is incremented every time. So ECX would be the index of the array, and ESI would be the pointer to the array. Does it make sense?
So in each iteration of the loop, that byte PTR ECX plus ESI reads one byte from the ESI, and then it moves one byte because we increment ECX.
So far we know that this is a loop which works on an array. Every time, in every iteration of the loop, we are accessing, we are copying the next byte of the array based on the index, which is ECX, into the EBX value. And then EBX is here being added to EDX. And then it goes up again for the next iteration.
And then we know that in the second instruction, we modify the value of EDX.
So it's basically a loop that does some sort of hashing algorithm, applies some sort of hashing algorithm on a string or on an array. So every time the result, the end result of the hashing routine is created, is placed in EDX. One byte from the new byte from the string or the array is copied to EDX, and EDX is added to the hash result of the previous iteration. And then if you haven't reached the end of the array, it just goes up again, gets another byte, rotates the result of the like hash, how to say, intermediate hash result or temporary hash result of the previous iteration in this instruction, and then adds the next byte to it. Does it make sense?
Is that clear?
So this was basically the end of content for this session. We put this, the last one, which is a bit more complicated, with this purpose in mind, that you go later after the session, try to understand every single line and have something a bit more unclear with you until the next session, so you can just play around and see what it does and like try to understand every single line. But if there's any question, I'm not sure if we have time or we are.
No, we are happy to take questions if people have any questions that they want to ask you, or if you want to give any further information for people to help learn more about it.
Okay, sure. High level, I need to catch up on assembly language, review the recording. Okay, good, sure. Very good. So let's have it until here for the first session. We will.
So just for everyone's knowledge, we will have next session with Noushin and Negar on 27th of August, where they'll be going much more in depth. Like it's like a next step from what we had today. So you guys have quite a bit of time in between to brush up or to learn more about it, and then maybe in the next session you guys can ask more questions from what you have learned, or any problems that you might have faced. I hope that is all right with the coaches here. It seems if there are no further questions, then I'll just wait for 1 or 2 minutes. If anyone does not have any further questions, then I will I think we can end this session. I'll just wait for anyone to. It doesn't seem anyone has any questions.
Thanks everyone for your time.
Well, thank you so much, Negar and Noushin, for conducting this session. I'm sure everyone must have learned something from this, and for those of who are already aware, it must have been a good refresher session. And also those who attended your workshop. So that must have been good. And I think from what everyone is saying right now, everyone enjoyed. And thank you. We really appreciate you giving your time and going through us, and also agreeing to do further sessions with us for this. What I'll do is for all the cadets who are in the call, so Negar and Noushin want your feedback on for the next session, like what would you like, a presentation style or more of a hands-on? So what I'll do is I'll put a poll or ask for your feedback in a Slack channel, and I'll get that feedback to them for their next session, and they can plan it according to what you all want. So but for now, I think this was a great session, so thank you so much. Thank you, Maeesha and Suzanne, for being at the back end and making sure everything runs smoothly. And of course, thanks to everyone who attended this session.
Thank you, everyone. We enjoyed. We hope you enjoyed as well. Looking forward to the next session.
Yes, we are.
Thank you very much for your time. Thank you for your time.
Thank you.
Thank you.
I think with that, we can close the session. Good night, everyone.